All right, so I wanted to end chapter 4 with a video talking about the connection between Egyptian multiplication and binary, using the techniques that we talked about in section 4.4. So let's do an example of Egyptian multiplication with 45 times 100. So just a reminder, from 4.1 we talked about this technique. What we do is we take the number 45 and put it in one column, the number 100, we put that in another column, and then we divide by 2 here, cutting off any decimals that appear until we get down to a 1. So 45 divided by 2 would be 22.5, but we just write 22. Half of that is 11. Half of that would be 5.5, we just write 5. Half of that is 2.5, we just write 2. Half of that is 1. Okay, then over here, I do the opposite. I double this number. So that gives me 200, 400. I keep going and doubling until I get down to the end. 800, 1600, 3200. Then what I do is in my left column, I look for any odd numbers. And the numbers in the second column that are adjacent to those odd numbers, I'm going to circle those because they're going to get added together. That's these guys right here. Okay, so I'm going to add these up. 3200 plus 800 plus 400 plus 100. You can add that up, you're going to get 4,500, which is very clearly what 45 times 100 should be. Okay, now what I'm going to do, let me kind of section that off over there, is think about what we've been doing in 4.4. When we're converting between number bases, one thing that we talked about, if we want to convert from decimal into some alternative number base, you're dividing by that base and then using the remainders to write out your new numeral. Well, here, since I'm dividing by 2, I'm going to think of this as converting the number 45 into binary. And the remainders are necessary to keep track of what my new number would look like. So 45, what do you get if you divide 45 by 2? Well, we know it's 22, but we get a remainder of 1. In fact, if you remember, in one of the previous videos for section 4.4, I said anytime you divide an odd number by 2, you get a remainder of 1. If you divide an even number by 2, you get a remainder of 0. So I'm going to go through and write what my remainders would be after dividing each of these by 2. That's odd, so that leaves me with a remainder of 1. This is even, so that's going to leave me with a remainder of 0 when dividing by 2. 11 is odd, so it leaves me with a remainder of 1. 5 is odd, that leaves me with a remainder of 1. 2 is even, which would leave me with a remainder of 0. 1 is odd, I get a remainder of 1. Okay? And then if you remember, the remainders, when read in reverse order, give me the binary form for that number. So this tells me that the number 45 is equal to 101, 101 in binary. 101, 101 in base 2. Okay? Now, what I could also do is write this in base 2 but in expanded form. And if you remember, what we said in expanded form is that binary is kind of special in the sense that it usually has a lot of zeros, and we're going to just neglect those zeros. In addition to that, any non-zero digits are automatically 1s. So in my expanded form, I'm multiplying each of my place values by, if it's not a 0, by a 1. And 1 times anything is itself, so it's kind of unnecessary to even write that. So let's think about what these place values would be. This is the 1s place, 2s, 4s, 8s, 16s, 32s. So in expanded form, if I simplify it a little bit, this is the same thing as 32 plus 16. Oh, no, sorry. Let me back that up. Let's not write it in those terms. Let's write them as powers of 2. I should keep it in powers of 2. So this is 2 to the 5th. This equals 2 to the 5th plus, there's a 0 here, so I don't need to write anything. That would be 2 to the 4th normally. 2 cubed plus 2 to the 2nd power plus, I'm not going to write 2 to the 1st power because there's a 0 here, but I will write plus 2 to the power of 0. Okay? And you can check this. This is 32 plus 8 plus 4 plus 1. That does add up to 45, so that would make sense. Okay, I'm going to leave that there for a second. Now I'm going to come over here and think about what I was doing in this second column. I was doubling. 100, again, we're thinking in terms of base 2 here. Notice 100 is the same thing as 100 times 2 to the power of 0, right? You wouldn't normally think to write it that way, since 2 to the power of 0 is 1, and 100 times 1 is just 1. But I'm looking for a pattern here, and this is going to help me. Now, if the process here is to double each previous number or to multiply it by 2, multiplying this expression by 2 just increases the exponent on that 2 by 1. So that's like 100 times 2 to the power of 1. Then if I double that, that's like 100 times 2 to the power of 2. And this would be like 100 times 2 to the power of 8. And this would be like 100 times, no, I said power of 8, sorry, 2 to the power of 3, which is 8. That's why I was thinking 8. 100 times 2 to the power of 4, and this is equal to 100 times 2 to the power of 5. Again, the exponent increases each step of the way because we're multiplying by 2 to get to each new number. Now, over here, if I were to rewrite this sum as with each number in this form, 3,200, that was the way that I wrote it down here. 100 times 2 to the 5th. 800 was 100 times 2 cubed. 400 was 100 times 2 squared, and 100 was 100 times 2 to the power of 0. That's the same sum, right? Just represented in a different way. So basically what I want to show is that multiplying 45 times 100 is the same thing as adding up these numbers right here. Now let's come back to this. Okay, let's suppose I wanted to multiply 45 times 100. Well, according to this, I showed that 45 can be written as the sum of some powers of 2 by converting it into binary and then thinking of how that binary would be written in expanded form. So I'm going to take this 45 and rewrite it this way. 2 to the 5th plus 2 cubed plus 2 squared plus 2 to the power of 0. And again, we're still multiplying that by 100. But now I know that I have the distributive property, which would allow me to distribute that 100 into each of those terms, which would look like this: 100 times 2 to the 5th plus 100 times 2 cubed plus 100 times 2 squared plus 100 times 2 to the power of 0. But that is exactly what this sum is. So that establishes that multiplying 45 times 100 is the same thing as adding these numbers, which is the same thing as adding the numbers in the second column corresponding to odd numbers in the first column. Okay? That's not what you would call a formal proof because we're using an example to illustrate this process, but you can see, hopefully, that there was nothing special about the numbers 45 and 100. I could have done this with any pair of numbers that I wanted to multiply together, and the same exact pattern would emerge. And this is the reason why Egyptian multiplication, or the more mathematical term, duplation and mediation, works the way that it does. Okay, that's going to be it for Chapter 4.